Start recording. Okay. So what you're seeing right now, that is the negative exponent code. So what we're going to do is to extend the program to also deal with what if the exponent of 10 is greater than 10 to begin with. This program was written a little bit while ago, so what we use as exp10 is your e10, exp2 is your e2, and so on. So the names of the members are just a little bit different. All right, so this is the previous one, and I argue that we can actually keep all of it exactly the same way, except we just need to add something new here. So I'm going to add a new piece of code here, which is looking at the exp10, but the exponent of 10, and as long as it is greater than 0, we're going to do something here. The reason why I can let the code remain as is because nothing that we have here at this point is going to hurt this particular project, for the positive exponent. Because what is left here, okay, if you look at the first loop, if you look at the first loop, it's not going to do anything because this one says as long as exp10 or e10 in your case is less than 0. Well, if you give it with e10 being positive to begin with, this loop doesn't even take place. Not even once, because it's a while loop. It checks the condition before it goes into the body of the loop. Is that okay? Does everybody understand why this would not bother the positive exponent program at all? Okay, so given that is the case, then we look at the code starting on line 52, which is basically just trying to maximize what we see as the exponent, but it was called the Mantissa before. So that alone is not going to do anything bad to the positive exponent part, because all it's trying to do is to make the exponent, or excuse me, it's going to make the coefficient from your perspective of Mantissa to use up all 64 bits, and it's going to adjust exp2 or e2 in your case accordingly, so we'll still be preserving the value being represented. Is that okay? Does everybody see how this is not going to be a problem? Okay. So inside the loop, starting on line 58, what we do want to do is to be able to decrement exp10 or e10 once per iteration. That is what we want to end up doing. So I'm going to put that code here because that's exactly what we want to be able to do. So we want to decrement it, but we also know in order to do that, we have to multiply the Mantissa in this case by 10, because these two actions would cancel out each other as far as the value being represented is concerned. So this way we're preserving the value being represented. But the problem is we don't know whether we have that space to multiply the Mantissa by 10 or not. So before this here, we have to make room to multiply the Mantissa in this case, but it is called the coefficient in your case by 10 again. Okay, so the question is, how do we do that? How do we make sure that, quote unquote, there's room to multiply the Mantissa or the coefficient by 10?
Divide by 2.
Yep.
Plus 1 divide by 2
with rounding, right? Exactly. So that's what we need to do. So now we need to have another loop here because we don't know how many times we have to divide the coefficient by 2. Most of the time it's 3 times, but occasionally it's 4 times. So we don't know exactly how many times. So that's why it's important to make it a loop. Now, if you want to be super efficient, you can always just have 3 times outside of a loop, and then have the 4th time to decide whether you need to do it or not as a conditional statement. That will optimize it just a little bit, because instead of checking the condition 3 or 4 times, you'll be checking the condition only once. Okay. Now, whether that's going to buy you a whole lot, I don't think so. So I'm not going to go for that optimization. Okay. So what I'll do is to basically say, okay, this is the way I write programs in CISP300, but I think it might be helpful to kind of put it here as well. So I'm going to say, while not enough room for another times 10, do the following. So the following is to have the Mantissa. Okay, so obviously this part should also be, oh, it's not letting me, okay, there we go. So this part obviously needs to be in comments as well because it's just reminding me what I want to do. So I encourage students in CISP310, which I have not taught for eons, to do this kind of thing when they're writing their code, because we want to capture what the intent is for the code, as well as what is trying to accomplish, instead of looking at the details first. Because looking at the detail first sometimes is not necessarily a productive way to write a program. So So now we have to look at this and go like, how do we know whether it has enough room for another multiplication by 10? So mathematically, what we are trying to say is if I multiply the mantissa, which is coefficient in your case, by 10 again, as long as that is less than um, u in 64 max, which we talked about last time, that tells me that we got enough room. But the problem with this code is there are 2 to the power of 64 minus 1 numbers as a 64-bit unsigned integer. That will be less than this number here. It's not going to be able to detect the condition that we want to detect, because by the time um, the 10 times the coefficient is exceeding the range of a 64-bit unsigned integer, this won't detect it. Is that okay? Because it would just kind of wrap it around because of the modulo 2 to the power 64 nature of having fixed width integers. So we look at this and say, it's not going to work. What are we going to do? Well, instead of doing this multiplication and then the compare, we can always just compare the mantissa or the coefficient with u in 64 underscore max divided by 10, because it accomplishes the same thing. Essentially, what we're trying to do is to divide both sides of the inequality by 10. And that's going to work. All right, so we'll put a divide by 10 here and then get rid of the multiplication by 10 here. That's algebra. Okay, division by 10 on both sides. And technically speaking, we got a few other things that we need to. No, this is all we need to do. Okay. Then the next question is, how do we have or how do we divide the mantissa by 2? Well, there are two things we know we need to do. The first one is to deal with the mantissa itself. And I'm going to do this for now. I know you already mentioned that we need to do the rounding thing, but I'm just going to do it for now, just to kind of capture what we need to do. And then every time we do something with the mantissa divided by 2, we have to do something about the exponent of 2. In this case, we have to increment, because these two actions will also quote unquote cancel out each other as far as the value that is being concerned is, um, as far as we're looking from the perspective of the value being represented. Are we still doing okay so far with this? All right. So now we look at the division and we go like, but Tack mentioned something about rounding, because if you just use integer division every single time and it's not exact, you're always looking at a result that can be smaller than or equal to what it's supposed to be. And these errors, because they're all biased in the same direction, they're going to add up. And when they do add up, you end up with a value that is significantly different from what it's supposed to be. So we don't want to do it this way because it doesn't take into consideration rounding. So now we have to do the rounding thing, which is basically doing the same thing as a division, but we have to add 1 to the mantissa first, or add 1 to the numerator first before we divide it by 2, because we concluded that the round of x is the same thing as the floor of x plus 0.5. But in this case, the 0.5 is easy to deal with because we're dividing something by 2, so the 0.5 can be represented as 1/2 of um, the denominator, and then we just add it to the numerator, and then that achieves the same thing as adding a 0.5. Are we good so far? All right. And I think that's it. This is the entire code. Now this time I don't have to worry about do we need to kind of bump up the Mantissa until it fills up all 64 bits? Because we are guaranteed of that already. Is that okay? Are there any questions about this code? Now, this is not the only way to do it. I have seen people doing this with a single loop and then with a condition inside. So they just, for each iteration, it just kind of alternates. It would do like 3 times of the division by 2 or 4 times of the division by 2, and then plus 1 multiplication by 10. So there are ways to organize the code so it doesn't look like a double loop. But to me, in my head, the double loop makes more sense. Are we good so far? So how do we test this, right? The next thing is how do we test this code? So what we are going to do is to look into the input, because that's what we did last time as well, is to go to the input, look at the command line, and then we specify -n, and then I would use the same example as in the assignment description, just so that I can catch it and see if I'm getting the same values at critical points of the algorithm. And I think it's E30, is that correct?
Yes.
Okay. All right, so that's the command line, and we're gonna set up. We'll put it in debug mode first, okay, and then we'll look into a few mechanisms that might be helpful to us. All right. So what we want to do is to look into the help manual, and the manual of GDB is built into GDB, so you can always just say help, which gives you some additional things that you can look into, like what do you need help with. So need help with is what we call a watch expression. So here's a watch expression. So watch and then a -L expression. A watch point stops execution of your program whenever the value of an expression changes. If -L is given, this evaluates expression and watches the memory to which it refers. So you can either give it a location and say, hey, if this location changes, stop and show me what it is. Now, in this class, it may not be very helpful. In CISP310, this can save your life. Because if you know that something is corrupting the value of a particular node or of a particular data structure, not the way you want it, you watch it. You just say, if something touches this location and try to change it, let me know. So when your program pauses, it will give you a line number, and then you can use BT or backtrace to find out how you got there all the way from main. In other words, it will show you the entire call hierarchy to end up at the point where it is about to change the value of the location that you're watching. So it's a very powerful debug technique when you have problems like memory corruption and stuff like that. This can really help. Okay, so that may not be what we want, because what I want is to display the value of certain things, like the entire PN, whatever PN points to, at certain times. So maybe what I can do is really just to put certain breakpoints in the program. So I can put one right about here, and we'll put one right after the loop, right about here. Let me see if I can set another one here. Yep, I can do that. All right, so let me get rid of this one. There. Oh, it doesn't want to go. Okay, that's fine. So we'll now go ahead and start the program. And this is our first breakpoint. And we want to see what is PM pointing to. So now it's time to double check and see whether this is what you're supposed to see. And so what we need to do is to switch over to the assignment description. Let me get back to that one. So it is about the technique. I'm trying to show you the technique of how do you check whether the program is doing what it is supposed to. So this is a floating point all the way to the bottom. And this is positive exponent. And in the description, I showed you, a few things. So right here, I think oh, okay, it's definitely not doing what we thought it should be doing, because this is taking a slightly different approach. It's trying to, this one maximizes, it's doing all the multiplication by 10 until it cannot do that, and then it will um, uh, do the other thing, to try to divide it. Okay, so so the question is, does the program end up with exactly the same result? Because if it does, it's still working. All right, so let me get back to the debugger and see if it ends up with exactly the same thing at the very end. So I'm gonna take out all the breakpoints except for the last one, and then we do the continue, and it's not working. This is great. If my program doesn't work, it's great for two reasons. One is I'm curious of why it's not working. It's like solving a puzzle. I gave myself a puzzle because I forgot about to do something. Two is I can now actually illustrate what debugging is about. Because otherwise, everything is going to be script, right? People would say, "Tach, you just script the entire thing. It's going to work. There's nothing exciting about it." Nope, I just made a poo-poo somewhere in this program, which happens a lot. Okay, trust me, I do make a lot of mistakes when I write programs. The question is, how quickly can I find those mistakes, and what tools do I use to find those mistakes? What techniques do I use, and what tool or what feature in GDB do I use? First thing first, it's in the infinite loop. So what do? Control C, okay? Because Control C or pause is going to stop the execution of the program, but it will tell you where you are. In other words, at least we know this line 65 is a part of the infinite loop, okay? So that is helpful because now I know the inner loop is somehow is involved in the infinite loop. So the next thing I need to know is, okay, show me what PN looks like right now. You go like, wow, that is, look at EXP2, is 5,757. And then EXP10 also changed a little bit, okay? But Mantissa is now becoming a 1. So things are definitely not going the way it's supposed to go. So now the question is, looking at the symptoms, of where do we start to fix the problem? So the program did not finish because EXP10 is stuck at 7. It never decrement any further, and EXP10 is guaranteed to decrement over here. There's no additional code in the loop to bump EXP10 back up again. All right. So that means somehow great. Happens a lot, but I think I remember enough of the problem of the symptoms to continue the reasoning. So now we say, okay, we somehow never got to here, which means the infinite loop has to be stuck here. Because if we got out to this point, then EXP10 will still be decrementing and eventually will get to 0, but it did not. So that means whatever the problem is within the inner loop, starting on line 61 and ending at line 66. So when you're in an infinite loop, you know you're in an infinite loop. Without a debugger, how do you analyze the code to find out what the problem is? Well, the first thing is one thing has to be right, has to be true, is somehow the condition remains true all the time. Is that okay? So now the question is, what are you doing within the loop that might change the condition up here? That is the question. So when we get down to here, we look at the Mantissa, we already know it was 1. And you go 1 plus 1 is 2, 2 divided by 2 is also 1. That is how it got stuck. Is that okay? And then the next question is, so that means I'm getting the Mantissa to be as small as possible. And then the question is, why am I making it as small as possible? Why is the comparison less than? That was the problem. Because what we are trying to do is to make room so that we can multiply the Mantissa or the coefficient by 10 again, right? So that means we're making the assumption that it might be over that limit already at this point. So it might be a huge number. I can no longer multiply the coefficient by 10. Okay, let me chop it by 1/2 and see if I have room. Meaning, I'm really checking to see if the Mantissa is continuing to be more than what it needs to be. So I was actually comparing in the wrong direction. in this case. Is that okay? So I can now go back here and fix the problem because what I really intend to do is to say, as long as I do not have enough room, I want to continue to divide it by 2. Is that okay? So what I just taught you, or what I just demonstrated, has absolutely nothing to do with computer architecture or assembly language programming. We haven't even started on assembly language programming in this class. But nonetheless, I still want to try to use this opportunity to introduce the technique or the thinking that can help you debug a program. Now, what are the chances that you will be doing assembly language programming after this class? Well, one, because you have one upper division class at a 4-year university that will also need you to write programs in assembly language. Okay, so that's one. But after that, most people would not end up programming in assembly language again. Okay, which doesn't mean the content of the class is not useful because it's still very useful for debugging C programs. But actually writing code in assembly language, not going to happen. But the chances of you having to debug your own code or somebody else's program and know what technique you need to use, that's pretty high, unless you do not want to, pursue the, developer, coder, software engineer route and want to go in a different route. Is that okay? So I do want to demonstrate these things. So now I know the program is, at least that problem is fixed. But I also want the program to resemble um, what the assignment is showing. Okay, so in other words, I want to go back to here and I want it to match this stuff here. So that means, the code that was trying to make the coefficient as large as possible, which is this code here, is interfering with that. So what I need to do in this case, okay, it's not necessary, but I'm doing it so that I can show you um, like how the code here is matching the result that is shown in the assignment. So now I'm going to go with a conditional statement and say if Pn is initially less, I mean, if exp10 was initially less than 0, this is what I do. Okay. Otherwise, switch to this loop here. I know the indentation is not working, not matching right now. So I will try to beautify, which some of you said did not work, but we'll see. There we go. Nope, did not work this time. Not this time either. All right, so that's okay. We can always kind of do it manually. Oh, this is painful. There we go. Oh, this is bad. It's missing the indentation of the brace. There we go. So it looks better. Okay, but I'm not gonna fix the other one yet because our focus is here. All right, so now we can go ahead and put some breakpoints here and see if the program is um, behaving the way we expect it to do. All right, so let's go back to debug and click start. And now we are at the first breakpoint. So let's go check out what is the structure the PN is pointing to. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. EXP10 is 22. EXP2 is 0. And let's go check out. Oh, okay, I clicked on the wrong key. So let's check this out. Okay, that's an exact match. Okay, this line is an exact match, which is good. Which is also the same as this line here. This is automatically generated, so it kind of behaves in a certain strange way. So now we go back to the program, which is over here, and we just kind of let it rip, which means we click continue, and then we let it go again. So this is after another iteration. We check out the whole thing again. So we look at what PN is pointing to, and we can see how it is 10 times of what it used to be, and EXP10 is now 21 instead of 22. So we check that against what we're supposed to see. You go like, wait, hold on a second here, Tech. I'm not seeing that. But that's because the trace is compressing some of the changes. So you're basically looking at a step that is working to that particular goal. So if we were to continue a few times, it would become like that. Is that okay? All right. So do you want me to continue with this, or do you want to kind of like, Tag, can you just kind of skip to the end? We want to see the program works, and that's all we need to see. Which way do you want to go? Get to the end? Okay. All right. Sure. We can do that. So we'll go here, and then we'll just take out these two breakpoints, and then put one at the very end of the function. And then we click continue, and now it is still stuck in it. Oh, no, it's all done. I just couldn't capture the end of the execution. Huh. Why is that? Oh, that's okay. Let me do it one more time. It just refused to stop at the breakpoint. Yep. All right, so let's see if I can put one over here. Nope. Okay. We could get to this one. It's just a matter of, I mean, not Logisim, but GDB not letting me put a breakpoint. All right, so let me see. What is the best way to set a breakpoint? Okay. It has stopped already because I can see the green line around the line, so that means it has already paused. So I can print out what it looks like at this point, but we are so far from the end that it's not gonna, it's not productive. Yep.
I just put the F print thing and put a break line there, and then
You could do that. Okay, I'm gonna show you another secret, technique here. It's called backtrace. So this is backtrace. What it shows you is this is how we got to E10 to exponent 2 is from main. So we can go back to main on line 204 and then put a breakpoint over there. So when we are done with this subroutine, we can then stop in main instead. So I'm going to do just that. Okay, so we go to line 204, which is right here. So we can put a breakpoint certainly right here. So right before we return from main, we can stop and then we can look at what end has at that point. So we'll now continue execution until that point, and now we can print out what end has. All right, so this is what n has, and we need to compare that to the log in the program. So we look at, so exp2 is 36, that's correct. And then Mantissa starts with 17, ends with 30. And I think that's what we are seeing. Yep, so that's exactly what we saw. So I feel somewhat comfortable that the program does what it's supposed to at this point. All right. Any other questions about this entire session? I'm so glad that I actually made a bug in the program accidentally because it allowed me to actually show you how to debug a program. Any questions? Any thoughts? Any questions? Comments? Nothing. Okay. Um, I just want to emphasize this is really important. Okay, it's not something that we teach in a class, unfortunately, but it really should be something that we do. All right. All right. So if there are no questions, we're going to move on to what I told you guys to try to do over the weekend, which is this spreadsheet here. And I said, let's figure out what's going to happen when the two input pins, change. One remains the same as before, the other one changed to a 1, and then do some analysis over here, and then eventually change the other one also into a 1, but the other, the EN remains as a 1 from before. So I hope you guys got a chance to do this, because as you are doing this, you are at least trying to understand the process of how to do this, and then you can have your answer. I have my own answer, and you can compare those two. Now, what if you see some differences, okay, between what you did and between what I'm going to do? Well, the first thing is you suspect Tag first. Maybe Tag made a mistake, because I do make mistakes, okay? Well, in that case, just raise your hand and go like, okay, Tag, I think you made a mistake here because my answer is not the same as yours. And then we can look into that together. And if we look into it together and it turns out that I was not wrong, then you might want to look into your own tracing and find out how you got the value that was different from my trace. Is that okay? So even though this is not an assignment per se, it is a chance for you guys to practice what I have introduced in class and to identify whether you might have some misunderstanding of the material or not. Is that okay? So it's really important that we all do this. All right. So I'm just going to move these two cells up a little bit, just to compact the table a little bit. And I'm going to highlight the one that has changed, which is this one here. So boldface this. And now we are going to go to, we'll take a look at what is going to happen first, okay? So the first thing we need to do is to do the propagation based on connectivity of the nodes, right? So if En is changed, which means this one is changed, then we are changing the first input of N2. We're also changing the second input of N1. So I have to make those, I have to mirror those changes to all the red columns. Okay, so this is red and this is also red. And then after that, I have to look into a propagational delay. And in this class, did we compress the node changes and the propagational delay into one row, or do we separate into two rows? I cannot remember how we did it.
I only remember just doing propagational delay.
Okay, so we do not have. Okay, that's fine. That's all good. All right. So now, so the question is, did I just touch something's input? Did I just touch the input of some of the gates? Because if I did, I need to look at the output of those things and see if they have changed. Does everybody understand what I just asked? Okay, so if that is what I'm asking, which column should I put an underscore to kind of as a placeholder so I remember to look at those particular outputs and see if they have changed? So just give me the number of the the destination of the columns.
So you should look at,
Well, first of all, we look at these guys, right? And then we look at those columns and we ask, is that an input of a particular gate or device? What do you think about this one? Yep, because it belongs to N1, so that means the output of N1 is now under question. What about the other one that we also just changed, which is column G? Is column G the input of some device? Yep, so that means the output of N2 is going to be something that I need to figure out. So this is how I determine whose output do I need to investigate to see if they have changed. Is that okay? All right. So what would be the answer to your question? What about the output of N1? What would be the current value of the output of N1 now that we know one input is a 0, the other input is a 1? And the output would be a 1. Very good. Okay. So, oh, wrong place to put a 1. But I'm going to use a regular one, not a boldface, because it was a 1 before. So changing one of the input pins of M1 from a 0 to a 1 did not change the output to anything else. So that change just kind of stops here. Now we look at the other one. We look at the output of N2. So is the output of N2 going to change because of the first input pin also changing from a 0 to a 1? It's going to change because now both inputs are ones, so the output is going to be a 0. I need to, oh, okay, I see what the problem is because now I think I need to separate the rows. Okay, I'm sorry about this. I know this looks confusing, but I have to kind of put a PD here. This is my actual input change. So I just repeat everything from before. I do apologize for the not not putting this into consideration first. All right, so on row 9, this is the one pin that got changed. So everything else kind of stayed the same, right? So we just kind of copy everything from the previous row, 0, 1, 0, 1, and then 1, 1, 1, 1, question mark, 0, 1, and then question mark, and question mark. All right, so now we look at this 0 here, and we ask, well, the output pin of a device just changed. Because of node connectivity, how is it going to affect other ports of the other devices? So for that, you have two ways to do this. You can look at the color code and you say, oh, SR.R is going to change as a result because they belong to the same node. That's one way to do it. But for people who are more visual, you just follow the diagram. You look at the output of N2, which is right here, and you ask, where does it connect to? Oh, it only has one place it connects to, which is the R of the SR latch. So I can do it either way. I personally, for me, I just look at the color code and I just kind of use that mechanism. But for those of you who are more visual, you can look at the connectivity, look at the diagram, and just use that to help you decide what else is going to change because of this. Okay, so knowing that, we just go to the other green pin here and say, this is going to change because it connects, as a node, it connects to the output of N2. So this is also going to be a bold phase. And now we move on to the next row. After a certain delay, we look at the previous one and we ask, did we change the input pin of a device? And you only have to look at the things that are in bold phase. This one is not a concern because this is what originates the changes, so we're not too concerned about that. This is the quote unquote recipient of the change. This is the one affected by the change. So we look at this and go ask, is that the input of some device? Is R of the SR latch, is that an input? So now we have to say, I think we need to look at the output of the SR latch. Okay, so we put I use underscores as a placeholder to basically say, do we know something about these two at this point? Okay, so that's what I'm asking. So what do you think? Nothing else got changed because the green columns, there are only two of them. Okay, so the change is not going to propagate all over the place. So let's take a look at the Q pin of the SR latch. We know the SR latch has the S being a 1 and the R being a 0. How does that affect the output? It makes it this one a 0. It makes this one a 1. That is from the truth table of the SR latch. So if we go back to the truth table of the SR latch, let me make this bigger. All right, so if we go back to the SR latch discussion, this is the truth table. So now we have a scenario of having the S pin being a 1, the R pin being a 0. That will reset the Q pin and then set the NQ pin. So that's the truth table coming from the SR latch discussion. So I'm just utilizing the result that is displayed here. And then we continue our analysis with the spreadsheet here. So that's how we conclude, Q becomes a 0 and NQ becomes a 1. And they're both changed because they were unknown before. So I have to boldface both of these. Is that okay? I'm going to pause here and stop talking and see if you guys have any questions. Nothing? No questions? All right. So I'm just, I know there are no questions, but I'm going to just kind of make a few recommendations. So the first one is, it is important to understand the behavior of an SR latch by itself. Because we understand the mechanism of the SR latch, and we made a conclusion of what the truth table is going to be for the SR latch. So that becomes important, which also means, if you, from the note-taking perspective, it might be useful to summarize the behavior of an SR latch as a truth table and put it at one place of your notes so that it's easy for you to find it. I do not expect everybody to be able to remember, oh, I see this input is going to cause that output. But I want you guys to have a tool, within your own, in your disposal, so you can easily look that up, just as a quick summary. Truth table, the best thing about the truth table is it's easy to look at, and it's also easy to find the answer just by looking at the input. That's the output, or that's the behavior because of that input. All right, so assuming there are no questions, if you do have any questions, just go ahead and ask. So assuming there are no questions, I just changed two output pins at the same time. So that means I need to look at a node connectivity and say, okay, who else is going to change because Q just got changed? So fortunately, not too many. This is one of them. Okay, and then we ask, NQ of the S hall latch just got changed. Who else is going to change because of that? And because of the connectivity of the node, these are the only two that will be changed as a result. So you can see how, from the wiring perspective, Q just got changed. So that's why the Q pin is also changed as a result, because they're connected by a node. NQ of the SR latch just changed, but because it connects to the NQ as a pin, so NQ is also going to change as a result of that. All right? Everything else stays put. Okay? So for everything else, I'm just going to copy everything as is. Okay, so this is a 0, this is a 1, that's a 0, and a 0, and a 1 here. Okay, so what do I do next? I look at all the things that got changed, and I ask, is one of those things that got changed is an input pin to a device, so I need to look at the output. So you have to track down what got changed, right? Um, these two are not important. So column L and column M are not important because they are the outcome of the previous propagational delay. So that's already taken care of. Okay, that's not the concern. It is the other ports that got changed that will prompt the question of, did I just change the input of a device that has an output? So we look at the other, like column P and then column Q. Fortunately, column P and column Q are output pins. In other words, they are not the input of something else. They are basically like the terminal. This is it. This is the end of the entire circuit. So that means I have no other things that can potentially change because of this anymore. So that means this entire step is done. Are we good so far? All right. Since I did ask you to do one more step, I'm going to finish it. Okay, so the next step is to maintain EN as a 1, but change D from a 0 to a 1. So that means I have to boldface this one. And this is what I would call the input change, because I changed one of the input pins. And I want to know what's going to happen if I change that one input pin. So just like the previous time, I look at the D pin and I ask, if I change that input pin, what other ports will be changed as a result of that? Once again, you can either use the color scheme. In this case, we follow the gray columns, or you can use the connectivity because of the circuit diagram, because I just changed which one? D, right? So we look at the D pin and we say, okay, what does it connect to? It connects to the first input of N1, okay, we got that. It connects to the input of the NOT gate, which we know as N. So those are the two additional things, or two additional columns that are changed because of column N, the D pin being changed to a 1. So we identify all the gray ones, this one and this one. So both of these are changed as a result of the change to input pin D. Everything else stays put. Okay, so we just copy everything the way from before, 0, 0, and then a 1, and then a 0, and a 1 here. Now, after a certain propagational delay, what do we do? Okay, I want you guys to answer the question.
Find out what changed as a result of those input pins.
We're looking at mostly outputs, right?
Outputs.
Yep, exactly. I knew exactly what you meant. I just want to hear you say it. Yep, yep. All right, very good. So, so that means, where do I put the underscores? In other words, which output port am I concerned about at this point?
You're concerned with N1's output and N2's output.
Yep. That is correct. Yep. So these are the two that I need to figure out. So let's go for the first one first. Okay. Column C, the output of the NOT gate N, is it going to change? What is the value based on the input? Hmm? It's going to be a zero. Yes. So is that a change from what it used to be? Yep. So let's boldface. What about this guy? The output of N1, we now know that both inputs of N1s are ones. So what is the output of N1 when both inputs are ones? It would be zero. Exactly. Okay, so that's also a change from what it used to be. Is that okay? Do you guys understand how or why I label those things as boldface? Because they are changed from what they used to be. So now I need to also propagate these changes based on what the output of n connects to and also what the output of n1 connect to. So one thing at a time, right? N dot out, which is this one here, connects to n2 dot in1 based on the color, or you can follow the circuit diagram, and the output of n connects to the second input pin of n2. So once again, either way works. I just like to use the color thing because I can focus on just the table and I don't need to go, you know, switch between the spreadsheet and also the circuit diagram. But that's just me. I have been told that the way I process things is not necessarily the same as most other people, which is not a good thing. All right, so the other one is the output of N1. Once again, you can use the circuit diagram or you can just follow the color code. So in this case, it's supposed to go to the S pin of SR, which is here. So that one is also a change because it used to be a 1 and now it is a 0. All right, so I have now completed the propagation of changes due to node connectivity. Okay, it's just the way the thing is wired up. And then everything else stays put. Okay, so I'm going to copy everything else exactly the same from before. And now after a certain delay, I need to kind of ask that same question again. Did I just change the input of something so that I need to pay attention to the output? So we look at all the boldface, right? We look at these two are not the concerns, okay, because these two are actually originator of the changes. So I'm not concerned about these two. But this one is kind of a concern because it is the input of N2. So that means I probably want to figure out what is the current output of N2. And then this one here is the S pin of the SR latch, which is one of the inputs. So now I have to re-question the two outputs of the SR latch. So these are the underscores that I need to resolve with this particular step in the whole process. So can someone tell me what this underscore should be? What is the current output of N2, knowing that one input is a 1, the other input is a 0?
Should be a 1.
Should be a 1. Very good. Okay, so we put a 1 here, and we can see it used to be a 0. This is new. Let's boldface it. What about the output Q of the SR latch? So once again, the truth table that we were looking at earlier can be handy. I'm just going to move this one over here so I don't have to scroll around too much. So looking at this table, we are looking at the first row, right? Because S is 0, R is 0 as well. So that means both output pins should be 1s. So now we switch back to the spreadsheet and say, oh, okay, both of them are supposed to be 1s. This is not a concern because it was 1 before already. Not too concerned about it. This was a 0 before. It just got changed. So I put a boldface here. Is that okay? So this is how I process what happens after a certain propagation of delay. So the devices have time to respond to the changes of the input pins. Is that okay? What is the next step? The next step is node connectivity propagation. In other words, I look at the things that got changed and I ask, well, if the output of N2 is changed, how is it affecting the input of something else? Well, R is going to be affected, right? Okay, so this is going to be changed to a 1. And then we look at Q of the SR latch SR, and it only connects to the output pin Q, which is this one over here, that is also changed to a 1. So, we good so far? So this is the result of node connectivity, so that the output of something is now eventually changing the input of a bunch of stuff. Everything else stays put. Okay, so 1 0 1 1 0 1 0 0 1 1, and then also a 1. So now we give it a little bit of time. We call that the propagation of delay. And then we ask, well, did we just touch the input of something? So let's go through every single bold phase and ask that question. That's not the input of something. This is the output of N2. Not concerned. This one here is the input of the SR latch, which means we kind of need to look at the output of the SR latch again. So when we do that, we ask both, okay, because it's from the one single device, so we have to ask that question. We got one more column, which is here. That is not the input of some device. Not concerned about that. So now we only have these two questions to answer, which is what are the outputs of the SR latch now that we know the input has 0 for S and a 1 for R. So once again, I don't want you guys to remember this. That's a waste of neurons. So we just look it up. Okay, we got 0 and 1 like this. So Q is supposed to be a 1 and Q is supposed to be a 0. All right, fine. We'll just kind of go like this is supposed to be a 1, that is supposed to be a 0. This one was a 1 before, so it's not a change. This one was a 1 before, but now it is a 0. It is a change. Is that okay? Now what do we do? We look at node connectivity again. Okay, so we now know that the NQ output of the SR latch just changed. So the question is, according to the diagram, where does it connect to? Well, let's see. NQ is right here. It connects to the pin called NQ. So the pin NQ also need to change as a result of that. So we go to the NQ pin here and say, yep, you're changing as a result of that. Everything else stays put. Okay, exactly the same as before. 1 0 1 1 1 1. Okay, so now we ask, did we just change the input of a particular thing that has an output? Well, we just go through every single one and try to find out. So we look at M. M is an output. It's not an input pin. Not concerned. We look at NQ. NQ is a output pin. It does not have quote unquote an output. That's a terminal. Okay. When we get there, we just go like, okay, fine, but there's nothing else that we need to do. So that means we have now reached also what we call a steady state. There are no further changes to analyze any further. And this is it. This is the end of the entire exercise that I was asking you guys to do over the weekend. So this is already shared, which means you can now take this and compare this to what you did over the weekend. If everything matches exactly the same, or at least some people might have split the rows, so one row for node propagation and one node for the propagation of the delay. So you might end up with more rows. The question is, did you come to the same states after each step? If you did, great. If not, then you need to ask the question of how is it different? Why is it different? How is it different? Now, as to the why they're different, it's possible that I made a mistake. Okay, that's entirely possible. But you need to kind of look at yours, look at mine, look at the way I did it, and ask, did tech make a mistake along all of these steps? It's possible. Are we good so far in terms of the process of how to do this? Now, I do want to emphasize this type of reasoning is not just useful for something like this, okay? Because if you are going to become a developer, a coder, a software engineer, or system analyst, the chances of you having to analyze the propagation delay or the propagation changes of a circuit is 0%, okay? But the reasoning behind this whole thing is still really useful. Why? Because as a systems analyst, you may not be looking at input pins, gates, and so on and so forth. Instead, what do you have? You have your client. The client said, I'm going to change the specification of this system. Instead of having this as the output, I want this as the output. Or instead of, I want to be able to process, 20,000 transactions per minute, and I want to up that to 40,000 because I'm expecting my business to grow. That's a change, right? So what do you do as a systems analyst? Do you just frantically change everything and go like, oh no, we're gonna have to redo the entire thing? No, you track down what components of the specification of the information system has to do with the number of transactions to process. The security model may not be impacted at all, right? What the user interface look like may not be impacted at all. But how many computers do you want in the mainframe cluster? That might get changed. So once again, you're analyzing what change is going to affect what else immediately. And then you ask, how is it going to change that immediately? Okay, so let's just say the security model, let's just say that the cluster needs to be bigger now. Okay, you need more cores within the computer system to process all the transactions. So the next question is, do we need more RAM as a result of having more core? If so, how much more do we need? So you're looking at change propagation also in that particular scenario. It's just that you're not dealing with logic gates. You're looking at it from the perspective of all the different specifications, all the documents that you need to prepare and specify as a systems analyst. Because the key here is to understand the dependency between the components and how each component needs to change its output when its input is changing. That's all. So I'm trying to relate this to things that you might encounter in your future, but it has nothing to do with what is inside a computer. Because ultimately, it resolves to dependency tracking, which is also what a makefile does. Do you guys know what is a makefile? Okay, we got some nods and we got some turning heads. A makefile. Okay, I cannot spend too much time on this because I have already digressed enough as we speak. You might want to look this up. Okay, it's just called a makefile, or it's one word. Oh, okay, sorry, my bad. So it's a makefile, and um, what a makefile does is it specifies dependency. This .c file is responsible to make that .o file. This is how you do it. There's an action associated with it. Okay, now I end up with a bunch of .o files. What do I do? Well, this is an executable. It depends on these object files. How do I turn the object file into the executable? This command over here. So a make file is essentially spelling out the dependency between all the various files that you need in order to run a program. That's basically what it is. So what if you change a header file, a .h file? Well, the make utility program tracks down who is referring to that .h file. You guys need to recompile. And then it looks at all the executable and asks, which one of you guys depend on that object file? Okay, you guys need to relink, okay, to the new executable. Kind of the same thing that we are talking about here. You certainly do not want your make file to specify something that oscillates. That would be bad. Is that okay so far? All right. Because I don't want to teach the class just for teaching the class itself. I want to teach you guys things that are maybe at some point or most likely relevant to what you will be doing in your jobs. Because that's what I want to do. I want to prepare you guys for your job. I'm not here to only teach a class. All right. At least I don't want to see it that way. All right. So there's that. You can take a picture. You can take a snapshot. Just go to File, and then make a copy. So that you end up with a copy of this in case I delete the file in the future or something. You still have your own copy. But I think it's important to kind of, if you got everything right, your exercise and what you worked on was exactly the same as this, great, okay? If not, it is still great, okay? Because it is much better to discover that somehow my analysis is different from this. At this point, because there's no point to this homework assignment. It's just something that asks you to do over the weekend. So if you completely, like everything is wrong or you did not do it, There's no deduction of points whatsoever. But by doing this, you might discover something. They go like, okay, so I think I might have misunderstood this concept here, or instead of doing this, I'm supposed to do that. But realizing it now is much better than realizing it after exam two. So I really urge everybody to look at this type of exercise in this particular way. All right, so getting back to the module. Okay, so what we have done so far, let me go back to the table of contents. So what we have done so far is to illustrate how, well, just one or few scenarios of how the level sensitive D flip-flop gets its work done. So if we go back to the spreadsheet, what is it really illustrating? So to understand what is illustrating, what we do want to do is to only focus on the last step of every single phase, okay, or the last phase of every single step. I got it all reversed. So with this one, you can kind of ignore everything in between. So everything from column B all the way to column M, kind of ignore those for now because they're just the mechanism of how things are done. And I can do that easily. So I can just say from here to here, let's just hide those for now. There we go. Pretty neat, huh? So now we just focus on the end result, okay? So if your D flip-flop, if you know nothing about your D flip-flop to begin with, and you only change both input pins D and EN to zeros, you will still know nothing about the output. Because EN being a zero means it's not paying attention. It's just going to like, if I know nothing, I still know nothing because I'm not listening to you at all, okay? And when we change the EN to a 1, then it starts to listen. And when it starts to listen, the D flip-flop's job is to copy whatever D the input pin has to the Q pin. It really doesn't care much about the NQ, so it's just the Q pin that we care about. And you can see how once the EN pin turns into a 1, after 2 propagational delays, the state of the D pin is now mirrored at the Q pin. And that's the job of a D flip-flop, is to remember something when you ask it to remember. Okay? But then, without changing the EN, remaining as a 1, we decide, hold on a second here. I want you to remember 1 instead. Right? That's basically what we're asking the D flip-flop to do. And you can also see, eventually, it copies the 1 from the D input pin to the Q output pin. So what this is illustrating, without conducting any additional experiments, is basically to say, if the EN pin is a 0, it doesn't care about the D pin at all. You can flip the D pin all day long, nothing happens, okay? But as long as the EN pin is a 1, it will mirror and copy whatever the D pin has to the Q pin after 2 propagational delays. Now, does it do it immediately? No, not in the sense of nanoseconds. From our perspective, it seems to be instantaneous, but it's really not because it has to go through these intermediate states in order to get a copy done. Is that okay? All right. So what we're going to do today is to kind of have to look at the time. We're running a little short on time. So I'm going to skip the road taking thing, and instead I am going to go through an edge-sensitive D flip-flop. So the edge-sensitive D flip-flop is a little bit more complicated. It has 2 SR latches as its components. Okay, so we're now looking at SR latches as components of other things. It has 1 NAND gate that has 3 inputs, 1 NAND gate that has 2 inputs, has got clock. D is data, okay, so these 2 are basically the same thing. What we know as the D pin is the data pin here. Has a 1 single output pin, which is Q. And then the rest is just describing how the ports are connected. So the first exercise you can do before we meet again on Wednesday is to kind of construct the circuit in LogicSim. Okay, just based on the description, text description here, construct the circuit. The second thing you can do, which I really hope all of you have time to do, is to go through the change propagation analysis that we just did, but with this circuit. The initial state is going to be having the clock pin being a 0, the data pin also being a 0. So do that, find out what the steady state is going to be, and then you change the clock pin from a 0 to a 1, and then see what happens. Next one is do something like this. So basically, these are all basically built-in exercises that you can do. You can look at all of these in section 5.1, 5.2, and especially 5.3. And then look at these and then turn those into the exercise that I just did in class. Because that is one way for you to practice, to understand how the edge sensitive D flip flop works, and also at the same time to get familiarized with the process. Is that okay? So once again, this is not going to be a graded assignment, but I really want you guys to be able to do it because I think it will help reinforce the concepts. So beyond the edge sensitive D flip flop, we also have the something that's even more complex, and I did not even bother to specify this in text. So the question is, if we have EN as a level sensitive way to say, hey, D flip flop, I want you to pay attention, whatever is in the input pin D, I want you to copy that to your output pin Q. So with that already, why do we need a clock? So as it turns out, the clock is one additional control mechanism of when the D flip flop needs to change or mirror the input to the output. So EN is saying pay attention or not. That's what the EN pin is trying to say. But with only the EN pin, with a level sensitive D flip flop, you're basically telling the D flip flop to say, whenever the data pin changes, I want you to change the output pin. So if your input is changing, your output is going to be changing as well, as long as the EN pin is 1. Okay? Well, as it turns out, that is not really helpful inside the processor because we also want to be able to control the timing of when to make that change, when to make that update. That's what the clock is for. So the clock is basically saying to the device and go like, even though you're enabled and there's input data at the D pin, but don't do anything until the clock goes from 0 to 1. At that instant of the clock going from 0 to 1, that is the very short amount of time where the device would say, okay, I'm going to copy the data pin to the Q pin right only at that moment. After that moment, once the clock pin becomes a 1, even with the EN being a 1, you can change the input D all you want, and it's not going to change anything. Is that okay? So EN controls whether a particular D flip flop should pay attention or not, and then the clock is telling it when to update. Now, why is that important? Well, the reason why both of these are important is because inside the processor, there are many D flip flops that are connected together. Okay, their D pins are all hooked up together. So imagine the class is like that. Each one of you is a D flip flop. You're capable of remember a single digit, a binary digit, a 0 or 1. Okay? So if I say, I want you to remember, all of you are paying attention, hopefully right now. So you all have the EM being a 1, right? So if I say, write down a 1, all of you are going to write down a 1, which may not be what I want, okay? Because I may want just you to write down a 1, and then later I want you to write down a 0, and so on. So the EN, the individual EN pin of each D flip flop allows me to designate who is going to update. The rest of you can just ignore me. Is that okay? So it's kind of a spatial thing. The EN is kind of a spatial control of who should update. But then what you update may rely on somebody else's content. So I want you to update first, and then whatever your output becomes, he is going to copy that. And then whatever your output is, she's going to copy and so on. So I also need timing control. I cannot just say all the 3 of you listen to me at the same time and write down, because the timing is important because we have adders and other mechanisms in between. So that means I need to allow some time for other things to get this thing done and in order for a D flip-flop to remember something. So that's why we also have the clock pin here to control the timing. I don't want you to write down anything until I say that. Is that okay? So one has spatial control, that's EN, and then one has temporal control, which is the clock. So now I can designate which register or which D flip-flop in the processor to remember the input exactly at which instant of time. Are we doing okay so far with that? Okay. I'm just looking at the time. We still have 5 more minutes before the lab time. So maybe I should transition to the lab discussion so that you guys kind of know what is going to happen in today's lab, because we are getting back to the lab thing. So, all right. So the lab thing today has to do with other components inside the processor. So this is the first one. This is the second one. We're going to deal with the first one only today. And I will show you the questions. All right, so the first question has to do with what we call a multiplexer. And I want you to create the circuit first. And then I want you to accomplish what we want to do, which according to the question is I want the output pin Z to specify 1001 in binary. So all of these numbers are in binary. And then your answer is going to be combining the input pins of X and Y, X being the most significant bits, Y being the least significant bits, and in order for the multiplexer to output 0, 0, 1 as the output, and based on what is the input. This is called a multiplexer. So what are you going to do? Tag, you haven't even talked about what a multiplexer is in the class. Well, I did. Remember the island of Sodor? Or did I talk about that in this class? I think I did.
Talk about Thomas.
Yeah. Yep. So we did, right? So we did talk about what a multiplexer is. But the key to do this homework assignment is LogicSim itself, because the help of LogicSim also explains how things work. So you need to, all right, so let me get back to, oh, okay, that'll work. All right, so this is LogicSim. So one thing you need to do is to go to the library reference. And let me show you the library reference, which is here. And then you need to go to plexers. So plexers cover both multiplexers and demultiplexers. So you go to multiplexer, and this is what you need to read. Okay, it's a little bit on the longer side. However, I think you guys can do this. Okay, you can read this and then determine how to answer the question. In other words, you need to understand the behavior of a multiplexer in order to figure out what input pins, how you want to configure the input pins in order for the output to be what we want it to be. Is that okay? Does everybody know where to find the LogicSim documentation? Okay. Now, the reason why I want you to actually build the circuit, let me go back to the activity itself. Okay. I want you to build a circuit first, because if you have built the circuit already, you can play around with it, right? So you can open up the help or the reference manual on one side, and then exercise the input pins on the other side to confirm your understanding of the device of what a multiplexer does. A multiplexer is like a railroad switch where you have multiple incoming trains but only one outgoing tracks. So you have to say stop to all except for one train and say, you are the one going through this switch, everybody else has to stop. Okay, that's what a multiplexer is. So the control is, how do you control which track of the input connects to the output? That's what the gray dot is representing. That's a selector. The other one is an enable, which basically means if there are certain times when you don't want any train to go through at all. So you basically just say, sorry, this switch is entirely disabled, nobody gets to go through. So that would mean all the incoming trains have to stop. nobody can get through the track. So that's question number one. And then for question number two, it is about what we call a register. Um, I'm not sure. Yeah, that will still be okay, I think. All right, so I'm going to use up a little bit more time to explain a register, just so that this way you have enough information to start with. I did not anticipate how much time I would be spending to talk about um, the tracking of the propagation of changes. So this is basically what a register is. Each one of these components is basically a D flip-flop. They have the EN, which is the enable. They have the D, which is the data, the 0 or the 1 that you wanted to remember. There's the reset, which is not really important in this case, because if reset is a 1, you turn everything to a 0. So I can tell you in your assignment, the reset or the clear should be a 0. So I can give you that one for sure. And then you have the clock. So the clock is basically the same thing as what we talked about. You need a clock to go from a 0 to a 1 in order for a edge-sensitive D flip-flop to remember its thing. So the only difference between this diagram and the diagram up here is I turn this whole thing into just a block, and then for each block, it is responsible to remember 1 bit. So when the input data is 8-bit wide, I now need to use 8 D flip-flops, each one responsible um, of remembering 1 bit. So that's why if we have a splitter here, the 8-bit input pin D is split into 8 individual bits. Each bit goes to 1 individual D flip-flop. So each D flip-flop is only responsible to remember 1 single bit. So to answer that question, okay, that might take a little bit longer because I did not actually get to talk about a register, but you can go to the memory library and then go to the register, and this will give you a full explanation of how it works. The key concepts we talked about already, which is the EN, the enable bit, and also the edge bit, which is the clock bit. So those two we talked about in this class already. So the question that you need to answer in the so-called quiz, let me get back to that one, is describe how you can make E, which is the output pin, end up with 0, 1, 1. Your description should be step by step indicating the value of each input pin. So A, B, C, and D. I have no idea. Anywho, um, so these are your inputs. I want the output to be 0, 1, 1. So the question is, how do you configure the input pins in what order so that the register is going to output 0, 1, 1 as an output? So once again, you can build a circuit in Logisim, play with it, experiment after or interactively as you read the documentation here so that you can understand how a register works, because that's kind of the purpose of this particular lab activity. All right, so let me release it so that you guys can get on with it. All right, so to edit, and here's the access code is EDGY, EDGY. And I give you all the way till the end of the lab. And for this class, it's 1:20 p.m. Here we go. You should be able to access it now. And remember, the access code is EDGY or EDGY. Yes?
I don't think I have Java on this computer.
Yeah.
Oh,
I don't
I don't think
have
Java
Java.
is there anymore.
They took out Java?
It appears so.
Yeah.
Oh, okay. And that's not much we can do, can we? Because then you can't even run LogicSim. I mean, I can give you the HTML documents, but it's not the same as, if you cannot run it. Shoot. Well, we can move the entire class to the main lab. Hopefully, they still have Java installed over there. Or I can sit here. You guys can come back to ask questions, or I can just let you guys do whatever you want. But I cannot change I suppose I can change the due date to the next class. So that way, if you want to go to the main lab, I can go with you. If you We can't stay here because there's no Java here. Yeah, let's do it that way. Okay, let me change the due date.
I assume the lab doesn't even have it.
I don't know. It just feels weird that they removed it.
All right, so I'm going to changing the due date to October 19th, which is Wednesday at 10:30 a.m. So right before class. So now you guys got quite a bit of time to do it. There you go. All right. Now, for those of you who have your own laptop computer, you can still do it here. So if you want to stay here, I'm not sure what you guys want to do. Do you want to stay here or not?
What's the option on the other lab?
The other option is go to the main lab and do it. But I changed the due date already, so you guys can basically do it anytime you want. It's just that with me here, you can ask me interactively if you run into questions. So that's kind of up to you. I'm going to stay here for the entire lab duration. So if you guys want to stay here and do it, that's fine. If you want to say, you know, I don't have my own laptop, I cannot do it here, then you can go to the main lab and do it now, or you can do it whenever you want, as long as it is before the next class starts.
Yeah, I tried to install it and stuff.
No, it won't let you because
That's admin.
they lock everything down, even though they have a lot of other types of protection already.
Overprotection.
Yeah. Well, if you render a system unusable, it is ultimately very secure.
It's on my table now.
Decoration.
See you Wednesday.
Yep.